the basics, okay, why, you know, your car has a battery. That's where the energy initially comes to start the car, okay? But there isn't enough energy in the battery to keep running it. So what has to happen is that once the car starts, the engine drives a generator. Today we have alternators, but this regulator is designed for generators. Okay, the principle is the same, but few technical differences in it. But once the car starts, the engine drives this generator to recharge the battery, and then it powers the car's electrical system. It'll power the lights, all the other things that go on there. So why is it that you need a voltage regulator? Okay, there it is. Okay. Well, it's because the load, okay, well, the RPM can vary 10 to 1, first of all. So it's going to turn much faster at idle. You're going maybe 500 RPM. Top speed, you might be going 5,000 RPM. So your engine RPM can vary by something like 10 to 1. The electrical load can also vary by more than 10 to 1. The headlights are the biggest consumer on most of the cars that were aimed at here, but there are other things that can go in there. So at idle with the lights off, you're a couple of amps, and at the maximum load, they're going to be maybe 20 to 25 amps. Okay. Now the battery needs an almost constant charge voltage. The battery doesn't want to see this voltage go way up and down, and neither do the other things in the car. They all depend on this voltage being relatively constant. The other thing is the generator needs to be protected from overload. Okay, you could hang a bunch of lights on the output on the car, etc. You could try to overload this, and you'll get the generator too hot, and it'll melt the wires inside. You'll burn out the generator. Okay, and the final thing is that you need to disconnect the battery when the car is switched off. Okay, so there's three basic functions. Okay, you have to have a constant charge voltage. You need to protect the generator from overload, and you need to shut it off when the battery, when the key's off. Okay, so how does an electromechanical one work? Well, the generator has two sets of windings: a field winding and an armature. Okay, it's not done with permanent magnets; it's done with electromagnets on the outside. And those electromagnets make a magnetic field that the armature turns within, and that produces the output of the generator. Okay, so the armature turns it in the field set up by the field winding, and it actually produces more current than the field winding consumes. Well, you guys may recognize this, Tonstoffel. There ain't no such thing as a free lunch, right? And so how is it that we can get more current out of the device than we put into it? Okay, well, the answer is that the engine's turning it. Okay, so the energy from the generator actually comes from the engine. All this is a load on the engine. Okay, so if you look at that generator, a simplified version of this, here, bless you. Here are the electromagnets that make this field winding, here, the north and the south pole. And the armature turns within here. This is the armature. And there are a pair of slip rings. So as this turns, the slip rings keep the current flowing to the output, and they prevent the direction of the voltage from reversing. As you bring this guy around, the commutator here, the connections to that reverse in synchrony with the windings here, so you always get a positive output on the positive turn. So it's much easier to control that field winding, okay, because the current's much lower. It's about 10 times lower. There's a couple of amps at most flow in the field winding, and maybe 25 or more amps flow in the armature. So if you increase the current in the field winding, the armature output will go up, and if you decrease the current in the field winding, the armature output will decrease. So the control element on an electromechanical voltage regulator is very simple. It's a relay. When the generator output gets too high, the relay opens and disconnects the field coil. And here's how that works. Here's a picture of how that works. this relay here is powered by the output of the generator, comes up here, and if that voltage tries to get too high, it interrupts the current to the field winding, and the output of the armature will drop, and vice versa. When that gets too low, okay, it'll start to it'll pull back in again, and you'll charge. You'll get the higher current path in there. Your generator output will increase. Okay, so that's a simple on-off control. Okay, you can see. This relay just turns it on and off. So in that respect, it's a very simple, very basic kind of control, but it's used in a lot of applications, like in your house, the heater doesn't run halfway, right? The heater's either on or off, controlled by the thermostat. And that can give you acceptable control. Your refrigerator's like that, right? The compressor's not partway on or partway off. It's just either on or off, and then the temperature inside goes up and down a little bit. And you're actually lucky in that you've got this big bag of electrons sitting here in the battery that is much, much bigger than the output of the generator. So if the generator output moves up and down a little bit, the battery output doesn't really move a whole lot. Okay, so it's kind of a crude form of control, but it's acceptable. The big thing is it's cheap and it's simple. Disadvantages are it's not very precise. You're lucky to get plus or minus 5% with this, and you guys who have them are, I'm sure, familiar with bending them, trying to change the field, and trying to adjust the output. It's not really very stable. It changes with age. It has moving parts. Okay, a relay like that in there probably has a lifetime of a few millions of cycles, which sounds like a lot, right? I mean, the 10 million cycles, it'll take you a long time to count to 10 million. But in the typical control scenario, you might be going on and off 10 times a second. So that's only about 11 and a half days worth of continuous operation. So that's not really very long. You can imagine that you could make a couple long trips and use up a big percentage of that. Brian Jones probably drove that much just going across the country. He probably used half the voltage regulator on the way. So the other thing is it's hard to compensate the temperature. Batteries, you don't charge batteries at the same voltage in cold weather as you do in hot weather. Cold weather, they have to charge them harder because it's harder to start the car. They drain more. You have more electrical accessories on in the winter, typically, and so it's hard to compensate these for temperature.
Tom.
Yes, sir.
10 times a second the points are opening and closing?
In some conditions, yes. Okay, they might be less in others, but 10 times a second is not impossible. Okay, that's kind of a worst case. I mean, the truth is, you typically last more than that. You can imagine if you're going 50 miles an hour in 278 hours, you're only going to get 13,000 miles. Okay, so that wouldn't be very, very far. Around here, you probably don't average 50 miles an hour. So, but that's kind of a worst case scenario. But you can see that it's not that great. Okay, there's definitely a finite lifetime to that relay.
And 10 cycles a second is probably very close to real, because you have to remember that when it's up to the right voltage, it's right on the knife edge of being too high or too low.
Yeah.
And so it closes, and then milliseconds later it's too much and it opens.
Yeah.
And then milliseconds later it's too low and closes.
It builds up quickly.
10 is probably around right.
And
somewhere in that range.
As I always point out, 13,000 miles in England was more than 13 years.
Well, there we go. Exactly right. The distances were shorter.
They don't drive 1,000 miles.
That's right. Okay. So, and in the case of the mechanical, that actually is a good point, but because that's the relay that moves a lot. There's actually 3 relays I'm going to show you that are in here. That's the relay that moves on off. That one shatters like a set of play false teeth on a table. Okay. That probably faster than that actually. So that one goes a lot. There's also a current regulator relay. That one doesn't go on and off nearly as much, okay? That one only gets activated. That one, the coil sits in series with the battery voltage, and when that gets too high, it opens up and it shuts off the output of the generator to protect the generator from getting too hot and melted, okay? But that, you know, during the course of normal operation, that might not happen, okay? So that guy there, that current regulator relay, might not move, you know, 1/1000th the number of times this does. So that typically is not the one that fails. This is the one that fails, the voltage regulator, okay? Okay, again, it's cheap and simple. The disadvantage is that that relay has to carry the entire vehicle electrical load. That sits in series, so if that does fail, the car stops, okay, or actually the car doesn't stop. The battery begins to discharge, okay. So, and the last one I'll point out, this one over here, the cutout relay, that's just turned on and off when the generator starts producing an output. So all that does is when you fire the car up, it pulls in, and then it connects the generator to the battery. When you turn the car off, it disconnects the generator from the battery. So that one only goes once per operation of the vehicle. So that one typically is even less than this one. So this is kind of from right to left. Those are kind of your villains there. Okay, this guy the most, this guy not nearly as much, and this guy not even nearly as much as that one.